satisfying about watching things going around in circles? It's not just the fascination of a motion that repeats itself endlessly, but also there's the perfect symmetry of the circle itself. And so perhaps it's not surprising that the ancient Greek astronomers were determined to model the motions of the heavens entirely in terms of circles. And when the philosopher Aristotle heard about this, he said that's how it had to be, that the universe was in fact quite perfect, that the Earth was at the center of the universe and everything else went around it in a system of circles. Now these ideas of Aristotle were to dominate the thinking of man for about 1700 years. And it was Nicholas Copernicus who first dared to challenge these ideas of Aristotle. He said, it's not the Earth at the center of the universe, it's the sun, and everything goes around the sun. Nevertheless, even Copernicus still insisted that everything moved in circles. He too had a complex system of circles. It was only much later that Kepler pointed out that you could model the motions of the planets much more easily, not in terms of circles, but in terms of ellipses. Nevertheless, the deviations from circular motion are rather slight, and for many purposes, circular motion is quite adequate. And that's what we're going to do today. We're going to use the standard model of circular motion that you've met in Unit 7, and we're going to build up a model of planetary motion and see how it will explain the observed phenomena. Well, just what are these observed phenomena? To answer that question, we're going to leave the astronomers' gallery here at the London Planetarium, and we're going to go down to Selsey, to the home of the astronomer Patrick Moore.
Look up into the night sky, and you'll see a great many stars, and they make up the star patterns or constellations. And the constellations don't alter for year after year, century after century. They always stay the same. You'll always be able to recognize the Great Bear and Orion and the rest. It was natural then for the very early astronomers to imagine that the stars were small lights fixed onto an invisible crystal sphere high above our heads, so that as the sphere rotated, it would take all the stars with it. And that was a very reasonable model. The Greeks realized that there were some bodies, they noted 5, which looked like stars, but behaved in a most unstar-like manner. They didn't stay still. They moved around from one constellation into another. Of course, you couldn't see them traveling, obviously, but if you watched them from one night to the next, you'd soon notice the shift. And the movements were not regular. Sometimes these bodies traveled one way against the starry background, at others in the opposite direction. The Greeks called them wanderers, and our word planet comes from the Greek for wanderer. Today, we have a very different model. The solar system is made up of one star, the sun, and the known planets and bodies of lesser importance, such as the comets. The planets, which the Earth comes third in order of distance from the sun, go around the sun in orbits or paths which are almost, although not quite, circular. But if everything is so regular and so circular, then how can we explain the apparently erratic wanderings of the planets when you see them from the Earth? The only way is to construct a model. And to make things as easy as we can, we'll assume perfectly circular motion and uniform rate.
So let's begin with a single planet. Let's look at our Earth orbiting around the sun. If we adopt the kind of simplifying assumptions which were suggested by Patrick, we can model the motion of the Earth using the standard model of circular motion, which was introduced in Unit 7. Here then we have the sun, and there's the Earth. It maintains a constant distance from the sun because we're modeling its orbit as a circle, and you'll notice it's going around that circle at a uniform rate. Now we're actually looking down, as it were, on the north pole of the Earth. I can tell that because the orbit is being traversed in an anti-clockwise, in other words, what we call the positive direction. Let's now introduce x and y axes, and we can then consider the components of the Earth's position vector on these axes. Well, let's start by looking at the y component of the moving Earth. As the Earth goes around its orbit, this point on the y-axis is keeping pace with it. You see, they're both at the same horizontal level. And this second spot then is moving with the y component of the Earth's position. Let's watch this vertical motion by itself for a while. And what you see is a very simple oscillation. It's what's called simple harmonic motion, rather like a pendulum bob. The best way to see what this involves is to plot the graph of this vertical motion against time. So we'll introduce a second spot, following this first one up and down, but moving steadily to the right with time. Now you can see it traces out a path And that passage is, I think, fairly familiar. It is, in fact, a sine wave. But what sine wave? What are its parameters? Well, it's easy to see that the maximum height is just the same as the radius of the orbit. And if we start both spots back again at time t equals 0, remember now, for the Earth, one revolution is going to take 1 year. We start them off. The Earth goes round its orbit, and as the Earth completes one orbit, we complete one cycle of the sine wave. So in other words, what all this means is that the y-coordinate of the Earth's motion is given by the equation y equals r sine omega t, where r here is the radius of the Earth's orbit, and omega is the angular velocity of the Earth about the Sun. And it's positive because the Earth is going anti-clockwise. Well, how about the x-coordinate? We do much the same kind of thing all over again, but this time we shall look at the x-component of the Earth's motion. This spot now is moving along the x-axis, but it's keeping the same vertical position with the Earth in its orbit. And if we look at that horizontal motion by itself for a while, well, again, we just see the same kind of oscillation we've met before. Let's plot this motion against time and see what we get. This time it's going to move downwards with time, and the path it traces out is again sinusoidal, but there is a difference. You see, here we have a positive maximum at time t equals 0. What do you think that might be? Well, in fact, it's the cosine curve. And what that means is that the x-coordinate of the Earth's position is given by the equation x equals r cos omega t, where you remember r is the radius of the Earth's orbit and omega is the angular velocity of the planetary orbit. So here then we have the x-component of the Earth's motion as it changes with time, and there's the y-component. They're very similar oscillations, although they're out of phase. When that one's up there, notice this one was at the center. If we combine these two motions together, what we get is back again the circular motion of the Earth in its orbit around the Sun. What all this tells us is that the motion of the Earth can be described by a pair of equations. X is r cos omega t, and y is r sine omega t. These actually give us the position of the planet at any time t. What about velocity? Well, just as in Unit 7, if we want to find velocity, all we've got to do is to differentiate the expressions for position, differentiate with respect to time. If we consider the x-component first, we shall get x dot equals minus omega r sine omega t. This is the horizontal component of velocity. It's just the velocity of this point moving along the x-axis. If we differentiate the second equation, we get y dot equals omega r cos omega t, and that's the vertical component of velocity. It's, of course, the velocity of the other point moving along the y-axis. Well, let's now stop the motion of the planet in its orbit. And if we do that, we can exhibit the x-component of its velocity as this arrow, and the y-component of velocity as that arrow. And if we combine the two things together, we get the resultant velocity vector, which is in this direction tangential to the circle and of magnitude omega r. Now, we can quite easily demonstrate to you the fact that the velocity vector is always tangential to the circle. What we've got over here is a low-friction puck, and it's fixed to a point with a length of string. If we set the puck moving, it goes around in a circle. But just watch what happens when the string is released. Well, the puck flies off along a line tangential to the circle because the velocity vector was in that direction at the instant the constraint was released. Well, now let's move on from velocity to acceleration. If we want to get the components of acceleration, all we have to do is to differentiate the equations a second time. In the x direction, then, the acceleration is given by the second derivative of x with respect to time. That's just minus omega squared r cos omega t. That's the acceleration of this point as it moves along the x-axis. And then in the y direction, we have the acceleration minus omega squared r sine omega t. That's just the acceleration of this point on the y-axis. Let's now freeze the motion at an instant of time, and we can then show you the x component of acceleration, which is to the left, because this point on the x-axis is moving towards the center and it's speeding up. The y component points downwards, because this point is moving away from the center, and so it's slowing down. The resultant acceleration vector points towards the center of the circle. Well, that would be true at whatever stage in the orbit we'd stopped the motion. In the case of the Earth, of course, it's the gravitational attraction of the Sun which provides that acceleration, and it forces the Earth to move around the Sun instead of flying off along a tangent. Well, that then is the familiar standard model of circular motion. But Patrick hinted that there's something odd about the motion of the planets. Do you remember he said they're known as wanderers amongst the stars? Well, what did he mean by that? After all, there's no hint of any odd behavior in our model so far. Let's go back to the London Planetarium.
For even as we sit here now, Voyager 2 is moving further still into space, toward the edge of the solar system.
I said earlier that if you want to follow the apparently irregular movements of the planets in the sky, you have to watch them for night after night. And that's not always an easy matter. But here, in the London Planetarium, we can do some armchair stargazing. We can speed everything up and compress months into seconds. It's all done by means of this big projector. The two main globes look after the fixed stars. And the bodies of the solar system, that's to say the Sun, the Moon, and the planets, have projectors of their own. So let's see what the planetarium projector can show us about the movements of Mars. When you're in the planetarium, it's only too easy to imagine that you're under the real sky. The stars are there in their correct positions and with their correct brilliancies. But the planetarium sky can do things that the real sky can't. And in particular, we can speed things up. So let us begin by speeding up the Earth's rotation. And this means that the stars will cross the sky much more quickly than they actually do, in a period of only a few minutes instead of the real 24 hours. And there is Mars, looking like a bright star. What we will do is to wait until Mars reaches its highest point above the horizon. That's called culmination. And when Mars has reached this point, we will stop the rotation of the Earth, so the stars will then appear to remain stationary in the sky. Now, concentrate upon Mars. We are going forward in time, allowing each second to represent something like 4 terrestrial weeks. And to start with, we can see that Mars moves in a direct sense. If you know your star patterns, you'll realize that Mars is in the area of Libra and is traveling down towards Scorpio, the Scorpion, one of the most brilliant of the southern constellations. But this direct motion is not going to last for very long. Mars will gradually slow down, it will reach a stationary point, and then it will start to backtrack. And this is what we call retrograde motion. You can see what is happening. No wonder that the ancients called the planets wanderers. It must have been very baffling to them. But once again, this retrograde motion doesn't last for very long. Mars will again gradually slow down. It will reach another stationary point, and then it will start once more to move in its original direction of motion, away from the area of Libra, back toward the Scorpion. There's the stationary point, and now once again we have the usual direct motion. In fact, what Mars has done is to loop the loop. And that may sound very strange for a planet which is actually moving around the Sun at a more or less uniform rate. But is it any stranger than watching a cyclist apparently ride backwards? Well, of course, you're not going to be taken in by that. What's happening is that we are observing from a moving vantage point. And so, the reverse of our motion is superimposed on everything beyond the barge. Now, the Earth, like the barge, is moving. And so everything in the universe, and that includes Mars, will have the reverse of the Earth's motion superimposed upon it. But unlike our barge, which is traveling in a nice straight line, and unlike those things that are just drifting by, both the Earth and Mars are traveling around the Sun. What we have to do is to see how a combination of those two movements can be explained to understand the phenomena we actually observe. And to do that, we must go back to those ideas of circular motion, which Roy introduced earlier.
Well, once more, we're faced with the need to construct a mathematical model. The first step is to specify the problem, which is to predict the apparent motion of Mars as it's seen by an observer moving with the Earth. Next, in step 2, we should make certain assumptions to simplify the problem and also to specify the model. Well, we certainly want to assume that both the Earth and Mars are point objects and that they're moving uniformly around the Sun in perfectly circular orbits. We're also going to suppose that the two orbits lie in the same plane. Actually, they very nearly do. We shall suppose that we can ignore also the spin of the Earth about its axis, which means that the observer's viewpoint doesn't rotate relative to the fixed stars. That's the way we saw things in the planetarium. Now, what we want to do is to find how the position of Mars varies with respect to axes fixed to the Earth and moving with the Earth. After all, it's the motion of Mars as seen from the Earth which concerns us. And that's why the axes need to be fixed to the Earth. And we'll fix them so that even as they go around the Sun, they still remain parallel to the original Sun-based axes. So what are the relevant variables? Well, these are simply the x and y coordinates of Mars with respect to axes fixed to the Earth. The next step then is to state the mathematical problem, to find expressions for these x and y coordinates. And that's precisely the problem, of course, that we've got to solve in the next step, which is step 4. Now, it's a very good idea to break any problem down into stages, particularly if some of the stages involve problems to which you already know the solution. Well, what do we know at the moment? What we do know are the equations of the Earth's motion relative to axes centered on the Sun. Let me remind you, here are the equations. The suffix e reminds us that the parameters r and omega are those of the Earth's orbit. Well, by analogy, we can at once write down the equations of the orbit of Mars about the Sun. First, we have the x-coordinate, and then the y-coordinate. This time, of course, we have a suffix m, just to remind us that the parameters are those now of the orbit of Mars. But what's this new constant, this epsilon, that's crept in? Well, at time t equals 0, we've assumed that the Earth is at the start of its orbit. But we must assume that at that moment, Mars may already be epsilon radians into its orbit, so that's where the extra constant comes from. Now comes the crucial stage. We've got to change from a system of axes centered on the Sun to a system of axes centered on the Earth, and they've got to move off with the Earth around its orbit. If you cast your mind back to the barge, there we saw how the reverse of the barge's motion was superimposed on everything around it. And Patrick told us how, in the same way, from our point of view here on Earth, everything in the universe has the reverse of the Earth's motion superimposed upon it. So if we take the Sun, for instance, well, we all know it appears to go around the Earth, and its apparent motion is just the reverse of that of the Earth relative to the Sun. This means that its position is given by these equations. They're just the same as we had before for the Earth relative to the Sun, except that we now have minus signs. So what they tell us is that from the Earth's point of view, the Sun appears to go around the Earth, starting from somewhere over here at time t equals 0, and still going in an anti-clockwise direction. Well, that's straightforward enough. Let's now see if we can do the same sort of thing to get the motion of Mars referred to these Earth axes. Now remember, unlike the Sun, Mars has got a motion of its own. And if we want to see how Mars appears from the Earth, we've got to subtract the motion of the Earth from the motion of Mars. And so, for the x-coordinate, we get this, where the first term comes from the motion of Mars around the Sun, and then we've got minus the x-component of the Earth's motion. In an exactly similar manner, we can get the y-component. We take now the y-component of the motion of Mars, and we subtract from it the the y component of the Earth's motion. Well, that's it. That was what we set out to find, because you see, we now have the x and y coordinates of Mars with respect to axes centered on the Earth. And so we've solved the mathematical problem. And this would enable us to predict the position of Mars as seen by an observer on the Earth at any moment of time. Well, the equations are all very well, but what do they actually mean? We've got to interpret this solution in some way. And that, of course, is just what step 5 in the modelling cycle tells us to do. Now, this is where our display really comes into its own, because you see, the computer can follow these equations and show us the subsequent motion. So we'll start by fixing the Earth and its axes in the center of the picture. Let's suppose this point is Mars. Let's make it move so its x and y components are in accordance with the expressions that we've just derived. Now, something rather strange happened there. It seemed to loop the loop. Does that perhaps explain why in the planetarium sky we apparently saw Mars going backwards? Let's watch it again. There very definitely is a period of retrograde motion. So our model actually seems to compare quite well with reality. In other words, we've completed step 6. Indeed, we've succeeded in our attempt to model the irregular motion of Mars as seen from the Earth. We're in a position to go on to the final step, that's step 7, and we could use our model to predict the position of Mars in the night sky at a given time, at least approximately. But that's all, after all, we expected to be able to do. It would be interesting to hear just what an astronomer thinks of our model. How well does it compare to reality?
All in all, it's fair to say that although the model of circular orbits in uniform motion gives you a good approximation, it's no more than that, and it certainly isn't accurate enough for our needs.
So what kind of changes would we have to make to our model to make it a reasonable one?
Oh, there are all kinds of complications. First of all, the orbits of the planets are not circular, they are elliptical, and that makes a tremendous difference. And then they're not all in the same plane. The path of Mercury is tipped by 7 degrees to the path of the Earth, and Pluto even more, and that makes a difference. And, of course, every planet produces a gravitational pull or a perturbation upon every other planet, and that has to be taken into account too.
But why do we have to have all this complexity in the model? Is it really necessary to go for such accuracy?
Oh, it's absolutely necessary. For one thing, if you're not absolutely accurate, your model is faulty, and you'll never know whether there's some fundamental hidden flaw there or not. And there are practical considerations too. We are now sending unmanned rocket probes out to the planets. And you've got to know exactly where the planets are and exactly where to send your probe. And if you make a very minor initial mistake, you miss your target planet, not by a few miles, but by millions.
So it really sounds to me as if we can never be satisfied with our model. We're always going to have to updating it as we find new facts.
Well, we're not satisfied at the moment for one very good reason. Something very odd about the outer solar system. You may remember that Neptune was discovered in 1846 because it was tracked down by the mathematicians. It pulled upon Uranus. And then Pluto was tracked down in the same way in 1930. But Pluto has been a real puzzle. It's turned out to be so small and so lightweight that it could not possibly have any measurable effect upon a giant planet such as Uranus or Neptune. So we've got to look for something else. And I suspect that there may be another planet out there. And in any case, there's a great deal about the solar system that we still don't know. Yes, indeed there is.